Imagine yourself beneath a quiet night sky. The dark expanse above is dotted with countless stars, and the hazy band of the Milky Way arcs overhead like a silvery river of light. The air is cool and still around you. Each point of light twinkles from across the cosmos, a reminder that the universe is vast and full of ancient stories that travel across time. You feel a sense of calm and curiosity wash over you. In this gentle journey, we will drift through space and time, exploring some of the deepest cosmic mysteries. With a soft, curious tone, we will wander from the dawn of the universe to the starry night above, unraveling secrets in a way that soothes and fascinates, helping you relax and drift into peaceful sleep. 1. Faster than light, the cosmic inflation of the Big Bang. From a tiny spark, the universe unfurled at unimaginable speed. This artist's concept illustrates the Big Bang's aftermath, when space itself stretched faster than light during cosmic inflation. Within a fraction of a second, the universe swelled from subatomic scales to astronomical size, a rapid expansion that set the stage for everything to come. In the beginning, there was a moment of extraordinary stillness and then a burst of motion. The origin of the universe, the Big Bang, was not a typical explosion, but the sudden appearance of space and time itself. In less than a heartbeat of cosmic time, far less than a single second, when the universe was a mere fraction of a second old, something caused it to expand faster than the speed of light. This sudden expansion is called cosmic inflation, a period when space grew unimaginably quickly. Picture the universe at that moment as an incredibly small, hot speck of energy. Then, in an instant, it doubled in size, then doubled again and again, at least 90 times in total. What started subatomic became macroscopic in a flash, racing outward so swiftly that distances between points grew faster than any light beam could travel. How can space itself stretch faster than light? The laws of physics say nothing can move through space faster than light, but space itself is more flexible. Space isn't a static emptiness. It can stretch and grow, carrying galaxies and light along with it. During inflation, it's as if the fabric of space became like an expanding balloon, and all the tiny seeds of future galaxies were carried apart on that balloon's surface. For a more poetic image, picture a tiny flower bud suddenly blooming into full blossom in an eye blink. That was how swiftly space opened up. No physical object broke the light speed limit locally. Instead, new space formed in between everything, pushing things apart. In those fleeting instants, our infant universe grew from smaller than an atom to perhaps the size of a golf ball, or even larger, almost instantaneously. The universe burst into being, stretching like a newborn, reaching out its arms. What could cause such a fantastic expansion? Astronomers and physicists still wonder about the trigger. The leading idea is that a mysterious energy field, sometimes called the inflaton field, flooded the early cosmos with a repulsive kind of gravity. Unlike normal gravity, which pulls things together, this energy caused space to repel itself, forcing it outward in a torrent of expansion. This strange field appeared and vanished in a cosmic blink, dumping its energy into the fabric of space. As soon as inflation ended, the expansion slowed to a more gentle rate. In that brief moment, however, the basic structure of the cosmos was imprinted. Tiny quantum fluctuations, slight random jitters in that inflating field, were stretched out as well, becoming minuscule differences in density that would later grow into galaxies and clusters of galaxies. We can think of cosmic inflation as the bang in the Big Bang, the dramatic opening act of our cosmic story. Inflation also helps solve some deep mysteries of cosmology. For instance, it explains why the universe looks mostly the same in all directions, a property called isotropy. By stretching everything so rapidly and uniformly, inflation made one region of space look like any other. It also explains why space itself is so nearly flat, neither sharply curved nor warped overall, and smooth on large scales. Though we cannot see inflation happen directly, its fingerprints remain. We see hints of it in the uniform glow of the cosmic microwave background, the faint afterglow of the Big Bang, which is spread almost the same in every direction, as if everything was mixed and smoothed by that early hyper-expansion. For about 380,000 years after the Big Bang, the universe was essentially too hot for light to travel freely. It was filled with an opaque, brilliant plasma, like a fog of charged particles. But as the universe expanded and cooled, electrons settled into atoms, and space became transparent. The bright flash from that epoch was released and is still around us today as the gentle microwave glow of the background sky. After that, darkness fell. No stars yet existed to shine. The stage was set by inflation and early cooling, but the cosmic dark ages had begun, a vast black canvas waiting for the first stars to spark to life. As you lie back and ponder this origin of the universe, imagine that tiny newborn cosmos quietly growing in darkness. There is no sound in this expansion, just a silent bloom of space and energy. It's a profound mystery how inflation happened, one of many puzzles scientists are still gently piecing together. But in the story of cosmic evolution, this was the grand opening chapter, a faster-than-light stretch that eventually allowed stars and galaxies to form. The intense flash of inflation gradually gave way to a calmer expansion. The hot, glowing universe began to cool and become transparent, and in that cooling cosmic ocean, matter started to gather. Over time, the first delicate structures formed from those seeds of density. Now we drift forward to ask our next question. Why did some parts of that early universe grow into galaxies, while others stayed nearly empty? 2. Galaxies and voids, seeds of structure in the early universe. A computer-simulated view of the cosmic web, the large-scale structure of the universe. Bright clusters and filaments contain countless galaxies, while dark regions represent vast cosmic voids nearly empty of matter. Gravity drew matter into the dense strands, leaving empty voids in between. Long after the tumultuous beginning, the universe had expanded and cooled enough for matter to start clumping together. At first, everything was a smooth blend of gas, mostly hydrogen and helium, spread across space almost evenly, but not perfectly evenly. There were tiny variations, little pockets slightly denser than their surroundings, and little patches slightly thinner. These slight differences were the seeds of cosmic structure. The denser spots had a bit more gravity, and they began to pull in material from their surroundings. Like a gentle tug in the darkness, the rich areas grew richer, drawing gas and unseen dark matter inward. Meanwhile, the less dense regions lost matter to their neighbors. They became the empty voids. Achingly slowly, over the course of hundreds of millions of years, the rich got richer and the poor got poorer. By around 1 billion years after the Big Bang, these gravitational gatherings had formed the first proto-galaxies and clusters, sketching out the initial strands of the cosmic web. Matter continued to flow into the dense pockets, where it eventually coalesced into the first stars, galaxies, and clusters. That matter had to come from somewhere, so as the cosmic web grew and evolved, the voids emptied out. Slowly, a cosmic web took shape. Imagine drifting far above, looking down at the universe. You would see long filaments like gossamer threads made of galaxies, intersecting at luminous knots where galaxy clusters form. Between these glowing filaments lie the voids, enormous dark bubbles millions of light years across where very little shines. In fact, these empty voids can stretch tens or even hundreds of millions of light years across, containing almost nothing at all. For example, the Boötes void spans roughly 330 million light years, yet contains only a few dozen galaxies. Astronomers have nicknamed it the Great Nothing, as normally that volume of space would hold around 2,000 galaxies. This shows just how vast and empty true voids can be. The arrangement of galaxies at these scales has been likened to a vast foam, the galaxies tracing filaments around bubble-like voids, with the voids themselves forming the hollow spaces in between. Why did some parts of the universe become these galaxies, while others remained almost empty? It all goes back to those tiny density fluctuations in the early universe. Inflation magnified those quantum ripples into slight hills and valleys of matter. The hills, with just a fraction more particles, began to collapse under their own gravity, attracting even more matter as the universe expanded and cooled. The valleys, with a touch fewer particles, gave up their matter to the surrounding hills and became emptier over time. Achingly slowly, the rich regions grew richer, and the voids grew emptier. As matter collected, the first stars in the universe began to ignite within those dense patches. In those primordial times, perhaps a couple of 100 million years after the Big Bang, the very earliest stars formed in small proto-galaxies, bringing light to pockets of the darkness. More and more gas fell into these growing clumps, and soon primitive galaxies took shape. Small, faint, and irregular by today's standards, but they were the seeds of the majestic galaxies we see now. Every galaxy we know, including our own Milky Way, likely started as one of these tiny early condensations of matter. Meanwhile, the voids between those matter-rich filaments grew more empty and dark. As galaxies pulled matter into their stars and halos, less and less remained in the spaces in between. It's poetic. As the rich areas of the universe grew, the poor areas became poorer in matter, creating a tapestry of light and emptiness. Yet even the voids are not completely empty. A few stray atoms, maybe a dusting of dark matter, and occasionally a dim, lonely galaxy can be found drifting through these deserts. But by and large, the voids are cosmic quiet zones where dark energy, a mysterious pressure we will discuss soon, has free rein to push space apart with little resistance. It's amazing to think that the difference between a galaxy and a void began with tiny random fluctuations in the newborn universe. If you imagine the early cosmos as a calm ocean, then inflation's end left gentle waves, some crests, some troughs. Over time, the crests became galaxies, bright islands of stars, and the troughs became the deep voids between those islands. Thus, some parts of the early universe blossomed into galaxy clusters and sparkling star cities, while others remained dark, vast voids. This grand design, the cosmic web, is the result of gravity's patient work on those primordial slight differences. As we float in our minds through this cosmic web, it feels quiet and immense. The nearest galaxies along a filament glimmer like distant city lights, while in other directions there is only darkness stretching for tens of millions of light years. These sprawling empty spans remind us that most of the universe is space, with matter sprinkled sparingly through it. Yet that matter was enough to form everything we see. In those early dense patches, galaxies took shape and began their own lives, spinning, merging, and evolving. The story of cosmic evolution raises another profound question. Within those young galaxies, what unseen influence was binding them together? There seemed to be an invisible mass sculpting the cosmos. It's time to explore this mystery of the unseen, the dark matter that fills the universe. 3. The dark matter, mystery, invisible mass with gravitational might. In the stillness of space, imagine a ghostly presence that neither shines nor casts a shadow, yet its gravity quietly sculpts the galaxies. This is the essence of dark matter, an invisible form of matter that permeates the cosmos like a hidden scaffold. We call it dark because it does not emit, reflect, or absorb any light. It's completely transparent and invisible to our instruments. And yet, even though we can't see it or touch it, we feel its pull everywhere. Astronomers discovered this mysterious mass through its gravitational effects. Decades ago, astronomers noticed that galaxies were behaving strangely. All galaxies appear to be wrapped in an invisible halo of dark matter, and this envelope is vitally important. Galaxies are rotating so rapidly that without extra gravity to hold them together, they would have been torn apart long ago if only visible matter were present. But they aren't torn apart. Something unseen is providing the additional gravity holding them together. That something is what we call dark matter. Dark matter has been poetically described as a gravitational ghost, a specter that haunts the universe. We can't see it, we can't touch it, but we absolutely sense its presence in the way galaxies and clusters move. Without it, our galaxy wouldn't exist. The Sun and all its astral companions would slip away from the Milky Way, drifting lonely into the void. In the 1970s, astronomer Vera Rubin observed that stars at the edges of spiral galaxies were orbiting much faster than expected, clear evidence that invisible mass must be present to keep those stars bound. All of this tells us that an enormous amount of unseen matter, far more than the ordinary matter, is lurking in and around galaxies. Every galaxy, including our own, is thought to sit inside a vast halo of dark matter that extends well beyond its visible stars. It's as if the glittering pinwheel of the Milky Way were embedded in a large, transparent cloud of something heavy that provides most of the galaxy's gravitational glue. How much of this ghostly matter is there? Surveys have concluded that as little as 5% of the universe is made of the familiar atoms that make up stars and people, while about 27% is dark matter, and the rest, around 68%, is an even more mysterious component called dark energy. In our own Milky Way, scientists estimate that dark matter outweighs normal matter by at least a factor of 10. Meaning the vast majority of our galaxy's mass is this unseen material. This means that all the shining stars, gas clouds, planets, everything we directly detect is only a small fraction of what's really out there. The majority of matter in the cosmos is this invisible dark matter. It doesn't glow or interact with light at all, and it passes through ordinary matter almost as if neither were there. You could be bathed in a sea of dark matter particles right now, and you wouldn't notice. They would slip through you without a trace. So what is dark matter truly? That remains one of the greatest unanswered questions, a true dark matter mystery. The leading hypothesis is that it consists of a new kind of subatomic particle, nicknamed a WIMP, weakly interacting massive particle. If WIMPs exist, these particles have mass, so they exert gravity, but interact so feebly with normal matter that they are essentially invisible and untouchable, save for rare collisions. They don't form atoms or emit light. They simply drift through the cosmic landscape, clumping together on large scales via gravity. Our only chance of detecting dark matter particles is by catching their very weak and very rare interactions with atomic nuclei. To do this, physicists have set up experiments deep underground. For instance, a large tank filled with liquid xenon that is monitored for tiny flashes of light. If a dark matter particle hits a xenon atom, it would produce a faint sparkle. So far, These detectors have seen no definite signals, highlighting just how elusive dark matter truly is. Another line of evidence for dark matter comes from gravitational lensing, the way massive objects bend the light of more distant galaxies behind them. We often see rings or arcs of light around massive galaxy clusters, indicating gravity stronger than visible matter alone can account for. That extra gravity is provided by dark matter lurking in the cluster, warping space-time like a hidden lens. There's also the evidence from galaxy clusters themselves. When astronomers measure how fast galaxies move inside clusters, they find much more gravity is needed than what visible matter provides. All of this tells us dark matter must be there. Dark matter is different from regular matter in that it doesn't clump into stars or planets. It neither emits nor absorbs light, and it doesn't collide with itself efficiently. So it forms enormous, diffuse halos around galaxies. These halos provide the gravitational glue for galaxies and even galaxy clusters, holding them together in spite of their fast rotation and random motions. In effect, dark matter is the invisible backbone of the cosmos. Without it, the pattern of galaxies and galaxy clusters we see would likely never have formed. Surveys of the cosmic web indicate that dark matter filaments provided the scaffolding for ordinary matter to collect and build galaxies. A spectre across the universe, dark matter must be there, yet its nature is hidden from us. It refuses to interact with the normal matter we encounter every day. There are even some who questioned its existence at all, suggesting perhaps our theory of gravity needs adjustment. But as observations pile up, from rotating galaxies to lensing arcs and the growth of cosmic structure, the evidence for this ghostly mass is overwhelming. In many ways, dark matter is the invisible backbone of the cosmos. It holds the galaxies together, quietly anchoring the glittering structures of the universe. Dark matter is a ghostly presence in our universe. It is invisible to the human eye, and so far, even to the eye of science. And, almost like an emissary from a hidden world, it hardly interacts with the normal matter we know, except through the gentle tug of gravity. It's humbling to realize that most of the matter in the universe is invisible to us, a strong reminder that there is far more to reality than meets the eye. Scientists know dark matter must exist because of its gravitational grip, yet our detectors remain dry. This adds to the wonder of the night sky. It's as if an unseen architect shaped the cosmos, and we only see the glittering outer structure it left behind. Dark matter holds the cosmos together, a hidden scaffolding of gravity that underpins the stars, an invisible backbone of structure that we can only infer by its pull. Even though we cannot see this cosmic glue, we can appreciate how it quietly keeps galaxies intact, adding to the mystery and grandeur of the universe. Dark matter set the stage and provided a framework for galaxies to form, but dark matter itself doesn't shine. The actual light in the universe comes from stars. With this invisible scaffolding in place, the universe was ready to produce its first brilliant lights. Now we turn our attention to those first stars that pierced the cosmic dark. What were they like? And why haven't we seen one? Fourth, first light, the elusive population. 3 stars. Long ago, before our sun was born, before Earth even existed, the universe experienced its first morning. In that cosmic dawn, the first stars blazed into existence, bringing starlight to a cosmos that had known only darkness for millions of years. These primordial stars are known to astronomers as population 3 stars. They were unlike any stars that came after them, and their story is one of both grandeur and mystery. What were these population 3 stars really like? They formed from the purest of cosmic ingredients. The Big Bang left the universe filled with mostly hydrogen and helium, with just a tiny smattering of lithium. Unlike later generations of stars, which were born from clouds polluted with heavier elements like carbon, oxygen, or iron. The first stars had no heavy elements at all. They were forged from a pristine mix of hydrogen and helium. Because of this pristine composition, scientists believe these stars grew to be much more massive than most stars today. Lacking elements like carbon or oxygen, which help gas clouds cool and fragment, those early star-forming clouds likely formed extremely massive stars, giants among giants. Calculations suggest a typical population 3 star might have been tens or even several hundred times the mass of our Sun. Some theories even allow for stars up to 1,000 solar masses in exceptional cases. These would be true titans, enormous, hot, blue-white stars burning fiercely in the ancient universe. Imagine one of those first stars forming in a quiet, cold halo of gas. A behemoth, perhaps 300 times the mass of our Sun, coming together out of pure hydrogen and helium. Soon it begins to shine with a fierce blue-white light, millions of times brighter than our Sun. This newborn star floods its cosmic neighborhood with intense ultraviolet radiation, illuminating the primordial darkness and ionizing the surrounding gas. Now, imagine you could witness the night sky during this cosmic dawn. The heavens would look vastly different. There were no galaxies yet, no dense star fields, only an inky black expanse punctuated by the light of a few lone giants. You might see one of these enormous stars shining in solitary brilliance, its blue-white glow casting faint shadows in the primordial darkness. The sky would otherwise be nearly empty and starless, an eerie stillness compared to the busy starry skies we know. It was a simpler, younger universe with just a handful of first lights breaking the cosmic night. Because they were so massive, these first stars lived fast and died young. A star hundreds of times the Sun's mass consumes its nuclear fuel at a breakneck pace. While our Sun will shine for about 10 billion years, a population the 3 star might have burned for only a few million years, a fleeting mayfly of a star on the cosmic timeline. And when they died, they did so catastrophically. Many probably ended their lives as giant supernovae. In fact, the most massive ones may have perished as exotic pair instability, supernova, explosions so complete that the star was utterly blown apart, leaving no black hole or neutron star behind. These explosions would have been extraordinarily brilliant, briefly outshining entire galaxies, and they would have forged the very first heavy elements heavier than helium, and scattered them into space. The pure, pristine gas was thus enriched with new elements like carbon, oxygen, and iron for the first time. In a very real sense, we owe our existence to those first stars. They produced the raw ingredients for planets and life. The iron in your blood, the calcium in your bones, the oxygen you breathe, all those atoms were forged in stellar furnaces. The first stars began this cosmic alchemy, and subsequent generations built on it. We truly carry the ashes of those first stars in our bodies, since elements like iron were formed in those ancient supernovae. In essence, we are children of those early stars. The universe's first fireworks set the stage for everything that followed. Although these population 3 stars were the first to shine, none have been observed directly by astronomers today. Why have we never seen one? The short answer is that they are exceedingly rare in the present universe, if any still exist at all. Given their tremendous masses, they would have burned out billions upon billions of years ago. Any surviving population 3 star would likely need to be of relatively low mass to have such a long lifetime. But the conditions of the early universe favored the formation of very high-mass stars. Thus, Astronomers suspect that no true Pop 3 stars still shine in our cosmic neighborhood. Instead, what we search for are their echoes and remnants. Population 3 stars left subtle imprints on the chemical makeup of the stars that came after. For example, we have found a few ultra-metal poor stars in the Milky Way's halo, ancient stars with extremely low heavy element content, which might be second-generation stars, born from gas enriched by population 3 supernovae. We also detect their influence in distant galaxies. Astronomers using powerful telescopes have identified primordial galaxies so far away, and hence so far back in time, that their light shows almost no heavier elements, a sign that population 3 stars had just finished enriching the gas or were perhaps still present. In one recent discovery, scientists found a distant galaxy with a pocket of pure, pristine helium gas, ionized but containing no trace of heavier elements. This is exactly what a cluster of massive, metal-free stars would create. Although astronomers still haven't seen a population 3 star directly, finds like this are considered indirect evidence that these first stars truly existed. One day, we might catch a direct glimpse. As technology advances, we may find an extremely distant, strongly lensed star, or the aftermath of one, that turns out to be a population 3 star. In fact, the Hubble Space Telescope recently discovered an individual star, nicknamed Earendel, that existed 12.9 billion years ago, possibly a later generation star, but an example of how we can isolate single stars at immense distances. The James Webb Space Telescope aims to push even closer to the era of the first stars. Each improvement in our observation is like peering a little deeper into the universe's past, chasing the first light that ever shone. For now, the first stars remain a theoretical treasure. We know they must have existed. Without them, the early universe's pure gas could not have produced the chemistry-rich cosmos we live in. They remain elusive, but their legacy is everywhere. The heavy elements they forged are the building blocks of planets and people. The light they emitted reionized the universe's hydrogen fog and ended the cosmic dark ages, making the universe transparent and ready for the formation of galaxies as we know them. As you relax and imagine those first stars, think of an ultimate cosmic dawn. Enormous blue-white stellar giants clustered in little proto-galaxies, shining over a vast darkness. They were lonely beacons, separated by great distances because space was already enormous even then. Their light was the first to break the cosmic night. When they perished, they left the universe a slightly richer place, chemically enriched, ready for the next generation of stars, galaxies, and eventually planets and life. Ancient Starlight began with them. The universe's early chapters were filled with light and chaos. Those massive first stars lived briefly, then exploded, seeding space with heavier elements that would become the stuff of new stars and planets. In time, more generations of stars and galaxies followed. Galaxies grew larger and often interacted with their neighbors. We may wonder, do these galaxies carry a record of all those chaotic events? Let's drift forward and explore how galaxies remember their tumultuous past. 5. Galactic memory. How galaxies recall their chaotic past. Every galaxy is like an ancient manuscript, its stars and structure recording a history written over billions of years. Though a galaxy doesn't have a mind to remember, it bears the imprints of its past in its very shape, motion, and composition. When we gaze at a spiral galaxy's graceful arms, or an elliptical galaxy's diffuse glow, we are seeing the end result of a long, eventful life, one that often includes collisions, mergers, and close encounters with other galaxies. The question is, how do galaxies remember those chaotic chapters? The answers lie in features both grand and subtle, in their shapes, in the orbits of their stars, and in faint streams and halos that serve as fossils of past unions. One of the most visible clues to a galaxy's past is its shape. Galaxies come in different forms: majestic spirals, smooth ellipticals, irregular lumps, and peculiar shapes. These morphologies often tell a tale. Spiral galaxies, like our Milky Way, have disc-like shapes with spiral arms and tend to have relatively orderly rotation. This suggests that for a long time, they avoided any catastrophic disruptions that would scramble their disk. They may have experienced smaller mergers or steady gas accretion, but nothing violent enough to destroy the spiral pattern. On the other hand, elliptical galaxies are more like giant, ellipsoidal swarms of stars with no distinct disks or arms. Astronomers believe many ellipticals are the product of major mergers, essentially collisions between two or more sizable galaxies long ago. In the violence of those mergers, the original structures, like spiral arms, would have been destroyed. Stars from the progenitor galaxies are thrown onto random orbits, creating a big ball of stars rather than a flat disk. Thus, an elliptical galaxy today remembers its chaotic youth through its very shape and star motions. The scrambled, smooth distribution of its stars is a lingering signature of ancient collisions. There are also irregular galaxies, which have strange, asymmetric shapes. These are often smaller galaxies that have been tugged and distorted by the gravity of larger neighbors. Their misshapen forms are like cosmic bruises, reminders of gravitational scuffles or near misses. Our own local group has examples. The large and small Magellanic Clouds, dwarf galaxies orbiting the Milky Way, are a bit irregular and show signs of disruption. Their shapes and streams of gas, like the Magellanic Stream, indicate they have been and are being gravitationally tormented by interactions with the Milky Way. Beyond overall shape, the motions of stars within a galaxy also carry memory. In a calm spiral, most stars orbit in the same direction within the disk. But if we examine the extended halo of stars around a galaxy, we often find stars moving in more random, eccentric, or even retrograde orbits. Many of those halo stars are thought to be immigrants, stars that originally belonged to smaller galaxies that the bigger galaxy devoured. When a dwarf galaxy merges into a larger one, its stars are dispersed into the larger galaxy's halo. They continue moving in the pattern of their original system, which might be quite different from the main galaxy's disk rotation. This creates stellar streams, long, thin trails of stars orbiting a galaxy's outskirts, all moving together along the path of the original small galaxy. Astronomers have discovered many such streams around the Milky Way and other galaxies. These streams are literally the ghosts of galaxies past, drawn out into space like cosmic tendrils. By mapping them, we can piece together the identities of the devoured galaxies and the timetable of their accretion. Picture one of these galactic encounters in your mind. A smaller dwarf galaxy strays too close to a big galaxy and begins to fall apart. Over hundreds of millions of years, its stars are stretched out into a long, tidal tail wrapping around the larger galaxy like a delicate ribbon of light. This stream of stars, once an independent galaxy, now slowly swirls and merges with the bigger galaxy's halo, a ghostly reminder of the dwarf galaxy's existence. For instance, one of the most prominent streams around the Milky Way is from the Sagittarius dwarf galaxy, which our galaxy has been in the process of shredding and absorbing for billions of years. As the Sagittarius dwarf orbits the Milky Way, tidal forces pull its stars away and smear them along a gigantic loop around our galaxy. We now see this as a vast arc of stars, the Sagittarius stream, wrapping around the Milky Way. It's evidence of an ongoing galactic meal, Our galaxy is currently cannibalizing at least this one dwarf galaxy, and in fact, several others, incorporating their stars. The chemical composition of stars also provides clues. Stars that formed in different environments have different mixtures of elements. When we find a group of stars in the Milky Way's halo that share certain unusual chemical signatures, like very low iron content or specific elemental ratios, it suggests they came from a smaller galaxy that had its own distinct history of chemical enrichment. Essentially, some halo stars are foreigners to the Milky Way, and we can identify their origin by their chemistry. This is a kind of galactic archaeology. Astronomers dig through the fossil record of star properties to reconstruct the assembly history of galaxies. By doing so, they have determined that our Milky Way ate multiple dwarf galaxies over time, each event contributing stars now seen in the halo or even in the dense bulge. Galaxies also retain subtle morphological clues of past collisions. Some massive elliptical galaxies have faint shell-like structures or ripples in their outer regions, concentric arcs of slightly higher star density. These are thought to form in certain merger events as the stars from the engulfed galaxy oscillate and phase wrap, creating shell patterns. Other galaxies might show a double nucleus or an off-center cluster of stars in the core, possibly the remnant of a smaller galaxy's core, or a sign that the central black hole has not fully merged yet. Even ring galaxies or oddball shapes are often indicators of an interaction. The striking Cartwheel galaxy, for example, with its ring-like appearance, likely formed when a smaller galaxy punched through a larger galaxy's disk, sending out ripples like a stone dropped in water. Those ripples spawned a ring of star formation. So, peculiar galaxies usually have a story of an interaction or merger behind them. All these clues, streams, shells, star motions, and shapes are a galactic memory. In a sense, a galaxy is like a living being that bears scars of past injuries. It remembers not with a brain, but with its structure and its stars. Astronomers, acting like cosmic historians, read those memories to unravel what happened. Galaxies like the Milky Way are still evolving. Even now, our galaxy is interacting with its neighbors. Apart from the Sagittarius dwarf, it's pulling on the Magellanic Clouds and drawing in their gas. And it's on a collision course with the Andromeda Galaxy, as we'll discuss next. The Milky Way's halo is full of streams and distinct groups of stars that were once other galaxies 33. Based on studies of star populations, we know this isn't the first time such cannibalism has happened 33. In fact, large galaxies grew primarily by merging with or accreting smaller ones. It's heartening, in a way, to realize that even amid chaos, a new order emerges and the galaxy carries on. The Milky Way's spiral disk survived some minor mergers and will likely be transformed by future major ones. Nothing in a galaxy's past is truly lost. Every interaction leaves behind a memory, and the galaxy continues, enriched and reshaped by its experiences. Galaxies are like quiet archivists of their own histories, preserving evidence of everything they've been through. Now that we know galaxies bear the fingerprints of their histories, we can envision some of those dramatic events themselves. Galaxies do not simply glide alone forever. They often meet and merge. It may seem surprising in the vast emptiness of space, but galaxy collisions happen frequently over cosmic time. In our next reflection, we will imagine these slow-motion crashes and discover how galaxies survive and even thrive through them. 6. Cosmic collisions, how galaxies crash and rise. Anew. An illustration of the predicted collision between the Milky Way and Andromeda galaxies as it might appear in Earth's sky 3.75 billion years from now. Andromeda, left, fills the view, and its gravity begins to distort the Milky Way, stretching our galaxy's spiral arms with tidal pull. Such galaxy collisions are a natural stage in galactic evolution, often leading to the two galaxies merging into one. In the vastness of space, one might imagine galaxies as isolated islands, rarely touching. But in truth, galaxy collisions are quite common. Our own Milky Way is on a collision course with the Andromeda Galaxy, the nearest spiral galaxy to us. In about 4 billion years, these two giants will begin to merge. From our perspective, nothing drastic will happen for a long time, but eventually, with catastrophic consequences in terms of galactic structure. Stars will be tossed into new orbits, some flung out into intergalactic space, others plunge towards the new center. The delicate spiral patterns of both galaxies will be destroyed, merging into one amorphous mass. But as cataclysmic as this sounds, this sort of process is actually a natural part of galactic evolution. In truth, this titanic merger will unfold over billions of years, a slow cosmic dance in the vastness of space. From far away, it would be almost graceful, a drawn-out melding of star systems. If future beings could watch the night sky, they would see Andromeda gradually growing larger and brighter over eons. Eventually, the two galaxies would begin to visibly distort each other. Andromeda's immense gravity stretching the Milky Way's spiral arms and flinging streams of stars into space. The sky might blaze with an extraordinary number of new stars forming as gas clouds collide and compress under the encounter's pressure. After a long turmoil, perhaps a few billion years of orbital dances and entanglements, the galaxies will coalesce into a single huge collection of stars, likely an elliptical galaxy with a diffuse, hazy glow. The familiar band of the Milky Way would fade, replaced by a gentler, all-sky mist of starlight from this merged system. Why do galaxies crash at all, given the vast distances between them? The answer is gravity. Galaxies are not static. They move through space, often bound in groups and clusters. Our Milky Way and Andromeda, for example, are both part of a small cluster, the local group, and are mutually attracting each other. Over time, this gravitational attraction draws them together despite the overall expansion of the universe. Interactions between galaxies, especially between a large galaxy and its smaller companions, are quite common, even today. Astronomers estimate that anywhere from a few percent up to a quarter of galaxies we observe show signs of currently merging or colliding with a neighbor, and almost every large galaxy has likely experienced multiple mergers over its lifetime. In the early universe, when galaxies were closer together, collisions were even more frequent. Small proto-galaxies merged to form larger galaxies in a hierarchical buildup. Despite the dramatic term collision, when galaxies run into each other, stars almost never collide directly. Galaxies are mostly empty space. The distances between individual stars are so huge that when two galaxies interpenetrate, their star populations pass through like ghosts. The stars simply begin, orbiting within the gravitational field of the newly combined system. Thus, during a collision, although the galaxy's shapes and structures are violently transformed, the stars themselves typically survive the event. It's the galaxy's structure and gas that bear the brunt of the interaction. When two galaxies collide, their clouds of gas do slam into each other, unlike the stars. These gas collisions and subsequent shocks can trigger an eruption of new star birth. In many galactic mergers, the galaxies undergo an intense burst of star formation, a starburst ignited by the interaction. In the midst of chaos, the merging galaxies light up with new stars forming at a furious rate. It's a poetic irony. Out of cosmic violence comes creation, as the turbulence causes gas to coalesce into brilliant young stars. In this way, a merger can trigger a brief, spectacular bloom of starlight, truly creation from chaos. The antennae galaxies, for instance, are a nearby pair of colliding galaxies well known for their colossal starburst. Huge clusters of massive blue stars have formed where the two spirals are smashing together, and long tidal tails of stars extend outward from the merging pair. The visual result is strikingly beautiful. The nickname antennae comes from the pair of starry tails that resemble insect antennae, stretching out into space. If one of the colliding galaxies is much larger than the other, the encounter can be rather one-sided. The larger galaxy might remain largely intact, aside from some added ripples or rings, while the smaller one is torn apart, its stars and gas assimilated into the bigger system. We call this process galactic cannibalism. In fact, our Milky Way is currently engaged in such a feast. It's in the process of cannibalizing several dwarfs, like the Sagittarius dwarf discussed, and others. If two galaxies are of comparable size, like Milky Way and Andromeda, we call it a major merger. Major mergers can drastically change galaxies, often destroying disks and creating ellipticals. Minor mergers, small galaxy into big galaxy, tend to layer the big galaxy with extra stars and perhaps thicken its disk or halo, but not ruin it entirely. The aftermath of a collision depends on many factors: the relative sizes of the galaxies, the angle of the collision, and how much gas they contain. Two spiral galaxies rich in gas can merge and fuel a spectacular starburst, then likely settle into a more elliptical shape, with much of their gas consumed or dispersed. Collisions between gas-poor galaxies, like ellipticals, might just result in a bigger elliptical with little new star formation. If a small galaxy hits a big spiral off-center, it might create a ring structure, as mentioned with the cartwheel example, or warp the larger galaxy's disk. It's important to note that even though collisions transform galaxies, individual stars and planetary systems usually survive largely unscathed physically. A star in a merging galaxy will simply find itself moving in a new gravitational environment. The chances of direct star-to-star impact are astronomically low. Our own Sun, for instance, would likely just migrate to a new orbit in the merged Milky Way Andromeda system, and future inhabitants of Earth, if any, might notice the sky change over millions of years, constellations shifting as new stars join the mix and others are scattered. Galaxies can actually thrive from collisions in the long run. The merger of two spirals might eliminate their neat structures, but can give birth to a larger, perhaps more diversified galaxy. Collisions can activate a galaxy's central supermassive black hole too. As gas is driven toward the center, it feeds the black hole, which can light up as a quasar or active galactic nucleus. These energetic events are short-lived on cosmic scales, but they highlight that collisions can create as well as destroy. Over time, the turbulence settles, and the merged galaxy may enter a relatively quiet phase, having grown in mass and perhaps sporting new features, like extended halos, shells, or multiple nuclei for a while. Our Milky Way itself is the product of past mergers, and far in the future it will merge with Andromeda and likely other neighbors, like the Triangulum Galaxy, to form one giant galaxy. Billions of years from now, an astronomer in that future, merged galaxy might see evidence of our current Milky Way Andromeda collision in faint star streams and a new distribution of globular clusters. They might puzzle over those clues, just as we puzzle over streams in today's galaxies. In the grand scheme of things, galactic collisions are part of the universe's life cycle. They are one way galaxies grow and evolve. Out of two galaxies, one often emerges, a bit like cells merging in cosmic biology. And remarkably, even through these violent events, stars, and any planets around them, mostly carry on, largely unharmed by the vast distances that keep them apart. Up to now, we have focused on matter and gravity, on stars, galaxies, and their interactions. But there is a deeper, more subtle phenomenon that governs the universe on its largest scales. Not only do galaxies collide and merge, but the space between galaxies is expanding. And, to our surprise, it's expanding faster and faster. A mysterious phenomenon, dark energy, is pushing the universe outward at an accelerating pace. Let us now gently contemplate what dark energy is and why it is driving the universe toward increasing emptiness. Imagine floating in a quiet cosmic void where distant galaxies are tiny and redshifted, slipping gradually out of sight. That is the realm of dark energy, the subtle agent of the universe's accelerated expansion. 7. Into the void, dark energy and the accelerating universe. Some 13.8 billion years ago, the universe began with a rapid expansion we call the Big Bang. After that initial burst of expansion, gravity started to slow the universe's growth. But the cosmos wouldn't stay that way. 9 billion years after the universe began, its expansion started to speed up, driven by an unknown force that scientists have named dark energy. What exactly is dark energy? The short answer is, we don't know. Interestingly, Albert Einstein once theorized something similar, a cosmological constant representing a repulsive force in space. He later dismissed it as his greatest blunder, not realizing that the universe actually does have this kind of built-in push. Now we know that approximately 68% of the universe is dark energy, a stunning confirmation that such a force exists after all. We do know that dark energy is making the universe expand at an accelerating rate, and that it currently dominates the cosmic energy budget, about 2/3 of the total. It seems to be a property of space itself, perhaps the energy of the vacuum. In essence, as space expands, dark energy creates more space, which in turn contains more dark energy, driving even faster expansion. You can think of dark energy as a sort of anti-gravity, or a pressure woven into the fabric of space-time. While gravity works to pull matter together, dark energy pushes space outward, making distant galaxies recede from each other at ever-increasing speeds. It was discovered only in the late 1990s by astronomers observing distant supernovae. They found that those supernovae were a bit dimmer, hence farther, than expected, suggesting that the expansion of the universe had sped up while their light was en route to us. This was a shocking revelation. Up until then, most scientists thought the expansion was slowing down, or at least coasting. Instead, it's as if an invisible hand started nudging galaxies apart more strongly as time went on. Dark energy is often likened to an unseen wind or a tension in space that repels. The nature of this wind, however, remains deeply mysterious. Some think it might be tied to the energy of empty space, also known as vacuum energy or Einstein's cosmological constant. If that's true, then every cubic centimeter of space, even the emptiest void, has a tiny amount of energy intrinsic to it. And as space grows, the total energy increases, fueling further expansion. Others have hypothesized a new field or force, sometimes called quintessence, that pervades space and changes over time. But so far, all observations are consistent with the simple idea of a constant vacuum energy density. Essentially, a fixed springiness to space that makes it expand faster over time. Gravity started out dominating the expansion when the universe was young and matter was dense, but as the universe spread out, matter thinned and gravity's influence weakened on large scales. Dark energy became dominant relatively recently in cosmic terms. We live in a time where dark energy has only recently overtaken matter. About 5 billion years ago, roughly when our sun formed, the universe's expansion stopped slowing and began to accelerate. Now, dark energy rules the dynamics of the cosmos. Approximately 68% of the universe is dark energy, 27% dark matter, and only 5% the normal matter that makes stars and planets. This has profound implications for the far future. In our current epoch, galaxies outside our local gravitational group are receding from us. As time goes on, they will recede faster and faster. Trillions of years from now, distant galaxies will be rushing away so quickly that their light will never reach Earth, or whatever remains of our galaxy. In effect, each local cluster of galaxies will become an island universe, increasingly isolated in a growing ocean of darkness. If intelligent life were to arise trillions of years hence in one of those far future island galaxies, they might see only their own stars, and none of the vast cosmos of galaxies we enjoy. The evidence of the Big Bang and the cosmic web would have slipped beyond their horizon. They would effectively be in a cosmic void, unaware of the greater universe that once existed beyond their galactic borders. On human timescales, dark energy doesn't change the night sky in any noticeable way. The accelerated expansion is extremely gentle, only apparent over billions of light years and billions of years. The stars and galaxies we see tonight will still be visible for generations to come, but slowly, inexorably, dark energy is dissolving the large-scale structure of the universe, pushing galaxies apart and making the voids ever larger. In the far future, our Milky Way, having merged with its neighbors, will find itself alone in a dark, silent expanse with no other galaxies visible in the sky. Dark energy stands as one of nature's greatest enigmas. We don't yet understand why it exists or what it wants. It might be an innate property of space-time, or it might indicate new physics beyond our current theories. It's humbling to realize that the dominant force in the universe is something we barely comprehend. The cosmos still guards its secrets, and dark energy is one of the deepest. Yet we do know how to describe its effect. In equations, it appears as a small, constant outward acceleration. In visuals, we imagine the universe's expansion as a graph that, instead of slowing down, bends upward with time, the signature of acceleration. One can also imagine an analogy. Think of a spacecraft coasting away from Earth, expected to slow under gravity, but then discovering a tiny engine on board that gradually ramps up, pushing the craft faster and faster into space. Dark energy is like that engine for the universe, a gentle push that grew strong over time. We find ourselves at a sort of cosmic midpoint in cosmic evolution, a time when dark energy is significant, but we can still observe other galaxies. It's fortunate in a way, because it means we can still see myriad galaxies shining in our skies and learn about the cosmos while the evidence is available. If we existed far in the future, the accelerating expansion would have carried many galaxies away from visibility. Right now, though, we can map the cosmic web, see the faint glow of the Big Bang's afterglow, and catch glimpses of extremely distant objects, all because we live at an epoch when the universe hasn't yet swept everything beyond our view. The discovery of dark energy, which earned scientists the 2011 Nobel Prize in Physics, reminds us that the universe's story isn't just one of things coming together, gravity forming stars and galaxies, but also of things being driven apart. In the grand balance, it appears that dark energy will win out over gravity on the largest scales. The ultimate fate of the cosmos, if dark energy remains as we see today, is likely an ever-accelerating expansion, a big freeze where galaxies become isolated, stars slowly die out, and the universe becomes an expansive, cold darkness. But that is trillions upon trillions of years in the future, an unimaginably distant prospect. For now, under our current sky, full of galaxies and ancient starlight, we can cherish the ability to glimpse so much of the universe's story. We are fortunate to witness a cosmos filled with brilliant galaxies near and far. And when we look at those distant lights, we are not just seeing space, we are looking into the depths of time. This brings us to our final reflection. Why does gazing into the night sky feel like looking into a memory? It's because the light that reaches us has been traveling for years, centuries, millennia, even eons. To look far out in space is to peer back in time. Let's explore this wondrous fact, that when you stare into the starry sky, you are seeing ancient starlight that began its journey long before you were born, long before Earth formed, and even, in some cases, long before the sun ignited. 8. Ancient Starlight. Looking into the night sky is peering into the past. The Hubble Extreme, Deep Field XDF, a long exposure image of a tiny patch of sky, reveals galaxies as they appeared up to 13.2 billion years in the past. Most of the galaxies in this image are seen in their infancy. When we gaze deep into the night, we truly see ancient starlight that left its sources long before Earth existed. On a clear night, when we look up at the stars, we are in fact looking back in time. The light entering our eyes from those distant suns set out years, decades, or millennia earlier. Every time we peer at something up there, we're seeing it as it was, not as it is right now. The vast distances in space mean that light, traveling at about 300,000 kilometers per second, takes a significant time to journey from there to here. Even the moon you see is as it was 1.3 seconds ago, the sun as it was 8 minutes ago, and Jupiter about 48 minutes ago. The nearest star beyond the sun, Proxima Centauri, shines to us from 4.2 light years in the past. Every increasing step of distance is a step further back in time. For the stars we see with the naked eye, the light travel times typically range from a few years to a few thousand years. The bright star Sirius, for example, is about 8.6 light years away, so we see it as it was 8.6 years ago. The star Betelgeuse in Orion is roughly 550 light years away, so the light hitting our eyes left that star around the year 1470, about the time of the Renaissance. The farther our gaze, the older the image we behold. When you look at the delicate hazy patch of the Andromeda galaxy on an autumn night, you're seeing light that left 2.5 million years ago, when early human ancestors were just beginning to walk upright on Earth. In effect, looking at Andromeda is like looking at a family photograph of that galaxy from 2.5 million years in the past. Now, consider the reverse. If an observer on a distant world 65 million light years away pointed a telescope at Earth right now, they wouldn't see our cities or people. They might see dinosaurs still roaming our planet. That's because the light reaching them today left Earth 65 million years ago, during the age of the dinosaurs. In their sky, our present day has yet to happen. Similarly, an alien in Andromeda, looking at the Milky Way, would currently see it as it was 2.5 million years ago, perhaps noting some changes in our galaxy that have occurred since. It works both ways. Just as we look out and see other beings' ancient light, any watchers out there would see our past as well. With our modern telescopes, we have pushed this time-traveling ability to the extreme. The Hubble Space Telescope pointed at a tiny dark patch of sky for days to collect the Hubble Deep Field, and later the XDF, revealing galaxies so faint and far that we see them as they were over 13 billion years ago, when the universe was only about 5% of its current age. The most distant object reliably seen by Hubble, before JWST, was Galaxy HD1, about 13.3 billion light-years away, meaning we observe it as it existed just 500 million years after the Big Bang. New observatories like the James Webb Space Telescope are pushing that boundary even further, detecting galaxies that existed only about 300 million years after the Big Bang. This means we are now glimpsing the universe's infancy, nearly 13.5 billion years in the past, when the first stars and galaxies were just beginning to form. It sounds magical, but it's actually straightforward physics. Light needs time to travel across the vast distances of space, so we inevitably see distant objects as they were long ago. In a very real sense, the night sky is a time machine. The ancient starlight arriving now carries messages from different epochs of the universe. The farther out in space we look, the further back in time we peer. We don't need science fiction to time travel. We do it with our eyes and our telescopes. The moon's subtle glow is a 1.3-second-old image. The sunlight warming our face is 8 minutes old. The light from the nearest big galaxy, Andromeda, is 2.5 million years old. And the light from the most distant galaxies we can see is over 13 billion years old, dating back to a time shortly after the universe's birth. Science fiction often imagines machines to take us to the past, but here we are, with the simple act of looking up, seeing the cosmos as it once was. As one famous saying goes, the cosmos is also within us. We are made of star stuff, and we are a way for the universe to know itself. When we observe ancient light, the universe is, in a sense, knowing its own past through our eyes. Every star is a kind of memory. Some stars in the night sky are relatively nearby, and their light is only a few years old. Others are thousands of light years away, and their light started its journey before human civilization began. There are stars we see in distant galaxies whose light left when our multi-celled ancestors were swimming in primordial seas. There are galaxies we observe whose light set out when Earth itself hadn't formed yet. And if we gaze deep enough, we can catch the fossil light from the Big Bang, the cosmic microwave background, which is the oldest light in the universe, 13.8 billion years old, a baby picture of the universe itself. This realization can change our perspective on the night sky. The twinkling stars are not just points of light, they are messengers from different times. The night sky is like a patchwork of various eras of history, all arrayed together. Some stars show us the universe as it was a few decades ago, some as it was centuries ago, some as it was thousands of years ago. And the faint smudges of distant galaxies show us the universe as it was eons ago. The farther you look, the older the memory. Knowing this, a sense of reverence often washes over stargazers. When you stargaze, you are literally witnessing the timeline of the universe spread out above you. The starry sky becomes a cosmic family. Album full of ancient snapshots. The Hubble Extreme Deep Field Image, and now even deeper images from JWST, allows us to see, in one view, galaxies across 13 billion years of time. Some are shown when they were infants, others in their teen years, some in maturity. An entire history of cosmic evolution in a single deep gaze. It also means that looking up is a form of archaeology. Just as archaeologists dig through layers of Earth to uncover the past, astronomers look at progressively more distant, and thus older, light to study the past. The universe has been sending us these records constantly. We just needed the tools and understanding to read them. As you contemplate the night sky, it's natural to feel a mix of awe and intimacy. We are connected to those distant times because we can see their light, and also because we ourselves are made of material forged long ago. The very atoms in our bodies were fused in ancient stars and dispersed across space, only to coalesce into new star systems, planets, and eventually life. In that sense, we are ancient starlight too, slowed down and given form. The photons that enter your eye from a star 1,000 light years away might have left that star during the early Middle Ages, traveled across the galaxy, and now gently trigger a reaction in your retina, allowing you to perceive that star. You become, in that moment, the final stop of a very long journey of light, a witness to a distant memory. Beneath the canopy of stars, one can't help but feel a kind of kinship with the universe. The atoms within us and the light that graces our eyes come from the same cosmic story. When we say we are made of star stuff, it's not just a metaphor, it's the literal truth. And when we gaze at the stars, we are looking into the places those atoms were forged, and even further back, toward the very birth of the cosmos. Tonight, we have journeyed through cosmic history, from the universe's explosive birth, through the delicate cosmic web of galaxies and voids, the invisible grip of dark matter, the brilliant first stars, the memories etched in galaxies, the dramatic dance of their collisions, the haunting pull of dark energy, and the silent witness of ancient starlight. Each mystery we visited is a reminder of how vast and wondrous reality is, and how fortunate we are to behold it. Now, under the blanket of night and the soft glow of ancient starlight, you can close your eyes with a sense of peace and connection. As you lie there, you are cradled by the very same universe whose mysteries we've been pondering. You are part of this grand cosmos, made of the same star stuff, witnessing the same ancient light. The cosmos above is vast and enduring, and you are a child of it, made of its dust, bathing in its light. As you drift to sleep, feel the timeless connection between you and the cosmos. Your breathing is calm and steady, like the rhythmic expansion of space itself, and each soft inhale connects you to the starlight that has traveled ages to reach you. The same stars that shone over our distant ancestors, and over the dinosaurs, and even over the first microbes, now shine on you. In their quiet, distant way, they watch over you. You are not alone in the dark. You are home, in a universe filled with stories and light. Good night, and may your dreams be filled with the gentle wonder of the stars.